The universe's first spark of life remains one of its most profound secrets. We are about to explore 30 radical theories on how living organisms first emerged, from cosmic seeding to quantum beginnings. By the end, you will see the very definition of life in a startling new light. Did biology ignite in the deep sea's fiery vents, or was it delivered to Earth from the stars? What do you believe makes something truly alive? Perhaps life did not begin in our planet's oceans at all, but was a passenger on an interstellar voyage. This is the core of panspermia, the theory that life's building blocks, or even life itself, arrived on Earth from the depths of space. Picture microscopic organisms, incredibly durable bacteria or spores, embedded within the heart of a comet or clinging to a speck of cosmic dust. These tiny stowaways could have survived a journey lasting millions of years, shielded from radiation and the vacuum of space, only to crash land on our young and welcoming world. The evidence for this cosmic seeding is both compelling and strange. Scientists have discovered extremophiles, microbes that thrive in Earth's most hostile environments, from boiling acid lakes to crushing ocean depths. These resilient life forms can also endure the extreme cold and radiation of space, suggesting that such a journey might indeed be possible. Then there is the famous Martian meteorite known as LH8 4001. This ancient rock, blasted from the surface of Mars by a powerful impact, eventually fell to Earth. Inside it, some researchers believe they have found tiny structures that resemble fossilized bacteria. While the debate over this evidence continues, the very possibility forces us to look upward. Panspermia does not answer how life first began, but it dramatically relocates the question. It proposes that the spark of life is not a local phenomenon, but a universal one, with the entire cosmos acting as a vast, interconnected nursery. So the next time you look up at the night sky, consider that we may not be mere inhabitants of Earth, but descendants of the stars themselves. But if life did not arrive from the stars, where did it come from? The answer might lie in a warm, shallow pond. This is the classic and enduring theory of the primordial soup. Picture Earth over 4 billion years ago, a world of vast, steamy oceans under a hazy, alien sky. In these waters, a rich broth of simple chemicals was simmering, a mix of ammonia, methane, and water vapor. Then a bolt of lightning cracks through the atmosphere, or perhaps the intense heat from a volcanic vent pulses through the water. This sudden jolt of energy sparks a reaction, forcing these simple molecules to link together in new and more complex ways. Over countless millennia, these random interactions could have produced the fundamental building blocks of all life, amino acids and nucleotides. In the 1950s, two scientists named Stanley Miller and Harold Urey put this idea to the test. They built a sealed glass apparatus to mimic the conditions of early Earth, filling it with water and the gases they believed made up the ancient atmosphere. Then they sent electrical sparks simulating lightning coursing through the mixture. After just 1 week, the result was astonishing. The previously clear water had turned a murky pink and brown, and analysis confirmed it was now teeming with amino acids, the very molecules that form proteins. This experiment was a landmark, proving that the basic ingredients for life could form spontaneously from non-living matter. Yet the mystery is far from solved. While Miller and Urey showed how the bricks of life could be made, they did not show how those bricks could assemble themselves into the first house, that first self-replicating molecule capable of growth and division. Debates still rage about the exact location, whether it was a sun-drenched tidal pool, a deep-sea hydrothermal vent, or the surface of a clay mineral that helped organize these molecules. The primordial soup theory gives us a powerful starting point, a recipe for life's raw materials, but the final cook, the process that turned those ingredients into a living cell, remains one of biology's greatest unsolved puzzles. Yet the sunlit soup of a young Earth was not the only kitchen available. far below the ocean's surface, in a world of perpetual darkness and crushing pressure, another candidate for life's cradle was brewing. This is the theory of deep-sea hydrothermal vents. Imagine colossal chimneys on the seafloor, known as black smokers, billowing clouds of superheated, mineral-rich water into the icy blackness. These are not serene environments. They are violent, dynamic places where the planet's internal heat meets the deep ocean. And within this chaos, scientists see a perfect setup for life's origins. The key is the chemical gradient. The scalding water from the vent, loaded with hydrogen sulfide and other dissolved minerals, meets the cold, oxygen-poor seawater. This stark difference creates a natural energy source, much like a battery. That chemical energy could have powered the very first metabolic reactions, long before photosynthesis ever existed. But where would these delicate chemical dances have taken place? The answer lies in the vents themselves. Their chimneys are not solid rock but porous, almost like a mineral foam. These tiny, interconnected compartments could have acted as nature's first test tubes, concentrating simple organic molecules and shielding them from the surrounding ocean. Within these protected pockets, the building blocks of life could have gathered and interacted, perhaps even forming the first primitive cell membranes on the surfaces of the minerals. The most compelling evidence for this theory is not just in the chemistry, but in the life that thrives there today. Entire ecosystems cluster around these vents, independent of the sun's energy. Giant tube worms, bizarre clams, and strange bacteria form a food web based not on photosynthesis, but on chemosynthesis. These organisms harness the chemical energy from the vent fluids, just as the theory suggests the very first life forms might have done. It presents a powerful vision, life not as a product of a gentle, sun-warmed pond, but born from the violent, energetic, and dark heart of the planet itself. But the leap from chemistry to biology requires more than just ingredients. It demands a molecule that can not only store information but also act upon it. This brings us to the RNA world hypothesis, a revolutionary idea that paints RNA as the original architect of life. DNA is the famous library of our genetic code, but it is a passive repository. Proteins are the versatile workers that build and maintain the cell, so which came first? The RNA world proposes a stunning answer: neither. Instead, a single molecule performed both jobs. RNA, or ribonucleic acid, possesses a unique duality. It can carry genetic instructions much like DNA, and it can fold into complex shapes that act as catalysts, speeding up chemical reactions just like proteins. This means a single strand of RNA could have served as its own blueprint and its own construction crew. The key players in this theory are called ribozymes. These are special RNA molecules that can cut, splice, and even build other pieces of RNA. In a world dominated by RNA, a ribozyme could have catalyzed its own replication, creating copies of itself over and over. This simple act of self-replication is arguably the very moment non-life crossed the threshold into life, beginning an unbroken chain that leads directly to you. The most profound challenge for this theory, however, is the molecule itself. RNA is a complex string of nucleotides, and how such an intricate structure could have assembled by chance from the probiotic soup is a massive puzzle. It is like finding a fully formed sentence spontaneously appearing from a bowl of alphabet soup. Scientists are actively searching for pathways, perhaps with the help of mineral surfaces or cyclical wet and dry conditions, that could have guided simpler chemicals into forming these first fragile RNA strands. The RNA world does not claim to have all the answers, but it provides a compelling framework for how the staggering gap between chemistry and biology might have been bridged by one remarkably versatile molecule. RNA is a complex molecule, and its spontaneous formation from a primordial soup seems almost too improbable. So where did it get its start? The answer might be found not in the water itself, but in the mud at its edges. The clay catalyst theory suggests that life's first blueprints were literally sculpted from the earth. Picture the warm, mineral-rich shores of early Earth, where certain types of clay, like montmorillonite, formed in shallow, cycling pools. These are not just simple dirt, they are intricate crystalline structures with vast, repeating surfaces. Their unique electrical charge acts like a powerful magnet, attracting and concentrating the simple organic building blocks floating in the water, such as nucleotides. Once held in close proximity on this mineral scaffold, these molecules were far more likely to link together into longer chains, forming the earliest versions of RNA. The role of clay was not merely passive. Its repeating atomic lattice could have served as a primitive template, a pattern that guided the assembly of these new molecules in an orderly way. This is a crucial step as it offers a potential answer to one of the RNA world's biggest puzzles: how replication could have begun before sophisticated enzymes existed. The clay itself, with its regular crystalline structure, might have provided the first crude form of a mold, forcing nucleotides to line up in a sequence that mirrored its own pattern. This is not just a philosophical idea, laboratory experiments have proven it. Researchers have shown that when they mix simple nucleotides with montmorillonite clay, the clay dramatically accelerates the formation of RNA-like chains, some reaching impressive length. This mineral scaffolding offers a compelling bridge, a way for chemistry to build complex information-carrying molecules step by step, without requiring a miraculous single-step assembly. It paints a humble yet profound picture of our origins, where life's first stirrings were not a sudden spark in the water, but a slow, patient construction project on a bed of common, life-giving mud. The surface of a glittering mineral might have been life's true starting line. While deep sea vents provide the energy, the iron-sulfur world theory suggests the spark itself happened on solid ground. Proposed by the chemist Gunther Wechtersheuser, this idea centers on pyrite, also known as fool's gold. Picture the rocky surfaces near a volcanic vent, coated with this metallic, brassy yellow mineral. Its crystalline structure carries a positive electrical charge. In the surrounding water, simple, carbon-based molecules would have held a negative charge. This created a powerful attraction, drawing these organic building blocks into close, ordered rows on the pyrite surface. This was not a random soup, but a highly organized molecular marketplace. Here, the chemistry gets truly fascinating. The formation of pyrite itself releases energy. Wechtersheuser proposed that this geochemical energy, not lightning or heat alone, powered the very first metabolic cycles. On this two-dimensional stage, a self-sustaining dance of chemical reactions could have begun. Molecules would react, their products would trigger new reactions, and the whole cycle would feed off the mineral's energy, creating a closed, self-reinforcing loop. This is what he called a pioneer organism, a living system without a body, defined entirely by its ongoing, self-perpetuating chemistry. It was metabolism first, a functioning chemical engine that later learned to build its own container. The implications are profound. This theory flips the traditional script of life's origins. Instead of genetic information like RNA coming first to direct metabolism, the metabolic network itself was the pioneer. Information storage and replication could have evolved later as a useful tool to stabilize and perpetuate this successful chemical process. The first life was not a thing, but a process, a fiery, mineral-driven cycle clinging to a rock. This paints a humbling picture of our own ancestry, not as a primordial cell, but as a chemical rhythm on a crystal surface, a pattern of reactions that one day learned to encapsulate itself and swim free. The idea of life as a cosmic accident is profoundly unsettling to some. What if our existence was not a random fluke but part of a grand, deliberate design? This is the theory of directed panspermia, a concept that pushes the boundaries of science into the realm of the philosophical. It suggests that an advanced extraterrestrial civilization, perhaps facing its own extinction, deliberately seeded the galaxy with the building blocks of life. They would have sent out robotic probes or durable capsules containing carefully selected microorganisms on a one-way mission to fertile young worlds. In this scenario, Earth was not a lucky winner in a cosmic lottery, but a targeted garden. The most famous proponent of this idea was none other than Francis Crick, the Nobel laureate who co-discovered the double helix structure of DNA. Crick was deeply troubled by the immense complexity of even the simplest life form. He found it difficult to reconcile how such an intricate information storage system could have arisen spontaneously from a probiotic soup in the short time available on early Earth. For him, directed panspermia offered a compelling, if radical, solution. Life was simply planted here. This theory does not answer the ultimate question of how life began. It merely shifts the origin to another time and place. Yet it raises staggering implications. If true, every living thing on our planet, from the smallest bacterium to the largest whale, shares a common, engineered ancestry. We would be part of a vast galactic experiment, or perhaps living in a nature preserve created by our cosmic parents. While this idea is currently untestable and sits firmly in the realm of speculation, it forces us to confront the deepest questions of purpose and destiny. Are we alone, or are we the carefully cultivated offspring of intelligence beyond our comprehension? Before genes could even be imagined, a simpler, more fundamental world may have already existed. This is the lipid world hypothesis, a vision of life's dawn where the starring role is played not by complex information molecules but by humble fats. Picture a chaotic probiotic soup rich with diverse organic molecules. In this watery mix, certain lipid molecules, with their water-loving heads and water-fearing tails, would have spontaneously arranged themselves into tiny, stable spheres. These were the very first bubbles, primitive cell-like vesicles that created a profound separation between an inside and an outside. This simple act of compartmentalization was a revolutionary leap. It meant that promising chemical reactions could now be concentrated and protected within these microscopic sanctuaries, shielded from the infinite dilution of the open ocean. A lipid vesicle was not just a container, it was the first private laboratory. But these bubbles were more than just passive bags. The specific composition of their lipid walls, the exact types and arrangements of the fat molecules could vary dramatically. Some configurations might have been more stable, better at growing, or more likely to split in two when they reached a certain size. This physical structure itself could act as a crude form of information, a heritable trait passed down not through a genetic code, but through the very shape and makeup of the membrane. A daughter vesicle that inherited a particularly robust lipid blend from its parent would have a survival advantage, initiating a primitive form of evolution based entirely on chemistry and physics. Within these protective lipid worlds, the building blocks for RNA and DNA could have been safely gathered and organized, allowing for more complex chemistry to unfold without being scattered. The lipid world presents a beautifully simple beginning where the drive to self-organize, to create order from chaos, was written not in a sequence of nucleotides, but in the fundamental geometry of a fat molecule, setting the stage for the genetic takeover that would follow. While lipids were creating the first cellular containers, a different kind of stage was being set under the sun. The zinc world theory transports us to the shallow, sun-drenched edges of early Earth's oceans where hydrothermal vents met the light. Here, in these warm, mineral-rich pools, crystals of zinc sulfide would have formed in sparkling crusts. This is not just a pretty picture, it is a potential power plant for life. Zinc sulfide crystals possess a remarkable talent. They are brilliant at absorbing the sun's ultraviolet light and using that captured energy to drive chemical reactions, a process known as photocatalysis. In a world without ozone to block it, the young sun bathed the planet in intense UV radiation, a force typically destructive to delicate molecules. But these zinc gardens would have turned this destructive energy into a creative one. Imagine these crystalline surfaces as nature's first solar panels, each one buzzing with captured light energy. This energy could have forced simple molecules like carbon dioxide and water to combine, building the more complex carbon-based compounds essential for life. This process provides a direct and elegant bridge, a way for non-living chemistry to harness the sun's power and begin building the intricate structures of biology. Most strikingly, this theory suggests that the very first energy-capturing systems, the ancient precursors to photosynthesis, may have begun not inside a cell, but on the surface of a glittering mineral. Life may have learned to eat sunlight while still clinging to a rock. It paints a vivid scene where the spark of life was not born in total darkness or by random lightning, but was gently, persistently forged in the illuminated, mineral-rich shallows, with zinc crystals acting as the crucial midwife between the sun's raw power and the first stirrings of a living metabolism. While zinc harnessed the sun's power, another energy source was quietly at work in the very ground beneath our feet. Radioactivity, a force we often associate with danger and destruction, might have been a crucial midwife for life. The radioactive beach theory proposes that the decay of elements like uranium provided a slow, steady simmer of energy across vast stretches of the early Earth's coastline. Picture ancient black sand beaches rich with uranium-containing minerals like uraninite. These grains were not inert, they were constantly releasing energy as they broke down, emitting a faint, persistent shower of alpha particles and gamma rays. This radiation did not just sterilize, it also created. As these particles shot through the shallow water, they would have smashed into simple molecules, breaking their chemical bonds. While this sounds destructive, it was also creative. The molecular fragments, now highly reactive, would have immediately scrambled to find new partners, forming more complex and stable organic compounds. This process offered a distinct advantage over more dramatic energy sources. Lightning strikes and volcanic eruptions are powerful but fleeting, like a single, brilliant flashbulb. Radioactive decay, in contrast, provided a constant, diffuse glow that could have persisted for millions of years, a reliable power grid for the slow, patient work of molecular assembly. Evidence for this comes from ancient geological formations, like the deposits found in Gabon, Africa, where natural nuclear fission reactors operated nearly 2 billion years ago. These sites prove that uranium can concentrate in nature and sustain long-term nuclear reactions, creating unique chemical environments. On an even earlier Earth, without the need for a full-chain reaction, the simple, widespread decay of radioactive minerals could have fueled the chemistry that led to life, turning the planet's first shores into a naturally irradiated laboratory where destruction and creation were two sides of the same coin. The machinery of life is built with parts that are almost all left-handed. This is not a metaphor, it is a fundamental and bizarre fact of our existence. Every living thing on Earth relies on amino acids that are almost exclusively left-handed and sugars that are exclusively right-handed. This property, known as chirality, means these molecules are not symmetrical. They have a specific handedness, much like your own two hands. In the non-living world, chemical reactions produce a perfect 50-50 mix of both left and right-handed versions. So how did life come to choose one hand over the other? This is the chiral puzzle, and its solution is vital. The enzymes and structures that make up a cell are like intricate locks and keys. If you try to fit a right-handed amino acid into a protein chain built for left-handed ones, the entire structure fails. A racemic mix, one with both types, would be a molecular disaster, a collection of broken parts that could never assemble into a working whole. One compelling idea points to the stars. The intense magnetic fields around spinning neutron stars can emit circularly polarized light, a kind of light that twists as it travels. This twisted light could have selectively broken down one form of amino acids in space more than the other, creating a slight imbalance in the molecular clouds that eventually formed our solar system. This pre-existing bias could have then been amplified on early Earth. Another hypothesis suggests the very rotation of our planet played a role. As Earth spun, the weak force from nuclear decay, which itself has an inherent handedness, could have influenced chemical reactions on its surface, giving a tiny but persistent advantage to one molecular orientation over billions of years. Or perhaps the answer is more down to Earth. The surfaces of certain crystals could have acted as selective templates, absorbing and concentrating only left-handed amino acids while ignoring their mirror images. This physical filtering process could have created local environments rich with the correct handedness, setting the stage for life's uniform assembly. Without this mysterious selection, the complex, interdependent systems of biology could never have gotten started. The homochirality of life is a ghostly signature of a decision made at the dawn of time, a fundamental preference written into our very chemistry that remains one of the most elegant and unexplained clues to our origins. The molecules of life may have fallen from the sky in a celestial hailstorm. Cometary delivery offers a compelling variation on the panspermia theme, suggesting that while living organisms might not have arrived intact, the essential ingredients for their assembly certainly did. Comets, those ancient, icy wanderers from the outer solar system, are far more than simple balls of frozen gas. They are cosmic treasure chests rich with complex organic molecules. During the late heavy bombardment, a period of intense asteroid and comet impacts around 4 billion years ago, our young planet was pummeled by these icy bodies. Each impact was a delivery, depositing vast quantities of water, along with amino acids, nucleic acid bases, and complex hydrocarbons directly into Earth's early oceans and atmosphere. This was not the seeding of life, but the stocking of its pantry on a planetary scale. The evidence for this is no longer just theoretical. The European Space Agency's Rosetta mission provided a stunning confirmation. After a decade-long journey, the Rosetta spacecraft rendezvoused with comet 67P, Churyumov-Gerasimenko. Its lander, Philae, and the orbiter's instruments analyzed the comet's composition, discovering a startlingly diverse cocktail of organic compounds, including the simple amino acid glycine and the key element phosphorus. This proved unequivocally that the building blocks of proteins and genetic material are present in these primordial objects. The question then becomes one of survival. Could these delicate organic molecules have withstood the violent heat and pressure of a comet impact? Sophisticated computer models suggest that a significant portion of a comet's icy core could remain relatively cool during a high-speed impact, preserving its precious cargo. This cosmic delivery service presents a powerful argument that the raw materials for life are not unique to Earth, but are a common feature of planetary systems, scattered throughout the cosmos by these icy messengers. Our planet's first chemistry set may have been a gift from the frozen depths of space. Even the most improbable event becomes inevitable given enough chances. This is the staggering premise of the multiverse theory, a concept that shifts the origin of life from a local mystery to a cosmic certainty. Across an infinite expanse of parallel universes, every possible combination of physical laws and initial conditions is playing out somewhere. In one universe, gravity might be too weak to form stars. In another, the fundamental constants prevent chemistry altogether. But in a vanishingly small fraction of these countless realities, the conditions are just right. Here, the random assembly of the first self-replicating molecule is not a 1 in a trillion long shot. It is an absolute mathematical guarantee. Our entire existence, then, becomes a simple question of location. We do not live in a uniquely fine-tuned universe. We live in one of the rare universes capable of asking why it seems so fine-tuned. This idea, known as the anthropic principle, suggests that the very fact we are here to observe our universe automatically filters for the conditions that allow our existence. It reframes the question from how did life begin to a more profound inquiry: in which of the infinite branches of reality did our particular story unfold? This connects the microscopic spark of biology directly to the grandest scales of cosmology, suggesting that life is not a fragile accident, but an inevitable feature of a much larger and perhaps infinite reality. Our planet may have always been more than just a rock. It could have been a living entity from the start. This is the radical vision of the Gaia hypothesis proposed by scientist James Lovelock. He saw Earth not as a passive stage where life simply appeared, but as a single, vast, self-regulating system. In this view, the origin of life was not a single chemical event in a pond or a vent. It was the dramatic moment when the planet's geology and its fledgling biology locked into a planetary scale dance, a feedback loop that began to actively maintain the conditions for its own existence. From its earliest days, life and its environment co-evolved, each shaping the other in a relentless drive for stability. Consider the young Earth with a sun that was significantly fainter. Simple climate models suggest our planet should have been a frozen ball of ice. Yet geological evidence shows it was warm and had liquid water. How was this possible? Lovelock argued that the first primitive life forms, perhaps methane-producing microbes, were already altering the atmosphere, thickening it with greenhouse gases to trap just enough heat. Their waste became the planet's thermostat. This is a complete inversion of the traditional story. Life is not a delicate passenger struggling to survive on a hostile world. Instead, it is an active participant, engineering the very air, water, and rocks to secure its own future. The entire biosphere behaves like a living body, with the oceans as its circulatory system and the atmosphere as its breath. This holistic perspective challenges us to see the line between the living and the non-living as profoundly blurred. The first stirrings of life were not the birth of a separate entity, but the awakening of the planet itself to a new state of being, one where it became, in a very real sense, alive. Viruses are not just invaders, they might be our ancestors. The viral world theory turns our understanding of life's history on its head, proposing that these simple entities are not mere parasites but ancient relics from the dawn of biology. We often define viruses as borderline life, requiring a host cell to replicate. But what if that dependency is a clue to their profound antiquity? Their structure is elegantly minimal, often just a strand of RNA or DNA wrapped in a protective coat of protein. This simplicity could represent a primordial form, a living system that existed before the first true cells ever formed. In this radical view, viruses are not hangers-on, they are pioneers. The evidence for this lies deep within their genetics. Scientists have discovered giant viruses like mimivirus, with genomes larger and more complex than some bacteria. These viral genes include parts of the protein-making machinery once thought to be the exclusive domain of cellular life. This genetic overlap blurs the line, suggesting a shared and very ancient past. The most startling implication involves our own cellular machinery. The enzymes that copy our DNA, the very core of our reproductive process, show striking similarities to those found in certain viruses. This has led some researchers to propose that this essential system was not invented by our cellular ancestors, but was instead donated by an ancient virus that infected the first primitive protocell. Instead of causing disease, this viral encounter provided the key tool for stable heredity, a gift that allowed life to complexify and flourish. Our entire evolutionary tree, with all its diverse branches, might have a viral root. This theory forces us to reconsider the very definition of life, suggesting that our cellular world was built upon a foundation laid by these enigmatic and perhaps foundational genetic entities. The same bizarre rules that govern the smallest particles in the universe may have been the hidden architect of life itself. Quantum biology is a frontier science that suggests the strange phenomena of the quantum world, like tunneling and coherence, were not just present at life's dawn, but were absolutely essential to it. We are used to thinking of life as a classical, macroscopic phenomenon, but its most fundamental processes occur at a scale where quantum weirdness reigns. Consider the enzyme, a biological catalyst that speeds up chemical reactions by a factor of millions. Classically, a molecule would need to climb over a significant energy barrier to react, a slow and inefficient process. Quantum tunneling offers a stunning shortcut. It allows a particle, like a proton or an electron, to simply vanish from one side of an energy barrier and reappear on the other, as if it passed through an invisible tunnel. This is not a metaphor, it is a documented physical process that enzymes seem to harness with perfect precision. The first energy transfer systems in protocells could have relied on a similar quantum trick. Quantum coherence, the ability of a particle to exist in multiple states at once, might have allowed the earliest molecules to explore countless chemical pathways simultaneously. Instead of fumbling through one reaction at a time, a molecule in a coherent state could test many possible configurations at once, finding the most efficient route to self-replication in a fraction of the time. This quantum search engine would have dramatically accelerated the pace of probiotic evolution, turning an impossible chemical lottery into a near-certain outcome. The spark of life may not have been a clumsy, random collision, but a delicate quantum computation, a fleeting moment of superposition where a molecule was both dead and alive, until it chose the path that led inevitably to us. The universe appears to be a perfect prescription for life. Its fundamental constants, like the strength of gravity or the mass of a proton, are balanced on a razor's edge. If gravity were just slightly stronger, the universe would have collapsed back on itself shortly after the Big Bang. If the force-binding atomic nuclei were just a fraction weaker, complex atoms like carbon and oxygen, the very elements of life, would never have formed in the hearts of stars. This observation is the core of the anthropic principle, a cosmological argument that forces us to confront our own existence. The weak version is a simple statement of selection bias. We observe a universe compatible with life because we are here to observe it. In the countless other cosmic scenarios where these constants are different, there is no one to wonder why. The strong anthropic principle, however, ventures into far more profound territory. It suggests the universe is not just accidentally life-friendly, but that its laws and properties must, in some way, inevitably lead to life. When we apply this to the origin of life, the implications are staggering. The chemistry that produced the first self-replicating molecule was not a random fluke in a chaotic system. It was the playing out of a cosmic script written into the fabric of reality from the very first moment. The laws of physics and chemistry seem predisposed to create complexity, to build molecules that can store information and catalyze their own replication. This fine-tuning suggests that life is not a fragile accident, but a fundamental feature of a universe that is, in a very real sense, meant to be inhabited. The debate then becomes a philosophical chasm. Is this apparent fine-tuning just an incredible coincidence in a single universe, or does it point to something deeper, a multiverse of infinite possibilities, or even a deeper principle of cosmic design that we have yet to understand? Our search for life has always been drenched in water, but what if we are looking in the wrong kind of ocean? The methane water world theory proposes a radical alternative, a biochemistry born not in warmth but in cryogenic cold. Imagine the surface of Saturn's moon Titan, a landscape with rivers, lakes, and rain, yet flowing with liquid methane and ethane at temperatures nearing -180 degrees Celsius. In such a frigid environment, water is not a liquid but solid rock, and the chemistry of life as we know it grinds to a halt. Yet methane itself can form complex structures and act as a solvent, a universal stirrer for chemical reactions, just as water does on Earth. This opens the door to a completely alien form of biology, one based on molecules that are stable in this deep freeze. On a world like this, the membranes of the first protocells would not be made of the lipids we use, which would turn brittle as glass. Instead, they might be built from acrylonitrile, a molecule detected in Titan's atmosphere that can form flexible, stable vesicles even in liquid methane. The very fabric of this life would be different, potentially using hydrocarbons for structure and relying on chemical energy sources like acetylene, raining down from the sky to power a slow, cold metabolism. This theory forces us to expand our definition of life itself. We are carbon-based, water-solvent life forms, but we may be just one single example in a much wider cosmic tapestry. The potential for such cryogenic life is not confined to distant exoplanets. It exists in our own celestial backyard, within the subsurface methane oceans of Titan or the suspected water ammonia lakes beneath the icy crust of Europa. The universe may be teeming with life, not as a single melody, but as a symphony played in many different keys. Before the elegant complexity of RNA took command, a simpler and sturdier molecule may have held the genetic throne. Peptide nucleic acid, or PNA, represents a fascinating hybrid, a potential missing link in the story of life. Its backbone is not the sugar-phosphate ribbon of DNA and RNA, but a chain of amino acids, the same building blocks that form protein. This simple change in architecture gives PN remarkable advantages for a primordial world. It is incredibly stable, resistant to the breaking and shattering that can plague more fragile RNA strands. And most importantly, it can do the one job that matters most. It can store and transfer genetic information by linking with other strands, just like its more famous cousins. This combination of traits has led to a compelling theory, the PN world. In this scenario, life's first genetic system was not based on RNA, but on this more robust and simpler molecule. PN could have served as the initial genetic scaffold, a stable platform upon which the first, clumsy acts of replication occurred. Its protein-like backbone means it could have formed more easily from the simple chemicals available on early Earth, without requiring the intricate and improbable assembly of a full RNA nucleotide. The true power of this idea is demonstrated in the laboratory. Scientists have shown that the components of PN can form spontaneously under conditions that mimic a prebiotic environment, something that remains a significant hurdle for RNA. Furthermore, these PN strands can act as templates, guiding the formation of both other PN strands and even RNA. This paints a vivid picture of a molecular handoff, where a stable PN world eventually gave rise to the more versatile, but initially harder to build RNA world. It suggests our genetic ancestry might run through a molecule that was part protein and part gene, a sturdy pioneer that laid the groundwork for all the life that was to come. Violent impacts that scorched the young Earth might have been forging life even as they seemed to destroy it. This is the theory of impact shock synthesis, where apocalypse becomes genesis. During the late heavy bombardment, our planet endured a brutal hailstorm of asteroids and comets, each collision releasing more energy than all our nuclear arsenals combined. These events vaporized rock and boiled oceans, creating a surface utterly hostile to any delicate chemistry. Yet within that fleeting moment of unimaginable pressure and heat, something remarkable could have occurred. The very shockwave of the impact, propagating through the simple gases and water of the atmosphere or a shallow sea, could have forced inert molecules like carbon monoxide and nitrogen to link into the complex organic compounds essential for life. It is a cosmic alchemy, transforming a blank slate into a rich chemical canvas in an instant. Laboratory experiments have proven this is not just speculation. Scientists use high-powered guns to fire projectiles at incredible speeds into mixtures that mimic the early Earth's atmosphere. Upon impact, the resulting shockwave consistently produces a suite of amino acids, the fundamental building blocks of proteins. This demonstrates that the destructive power of an impact carries within it a creative spark, capable of manufacturing life's ingredients from the most basic raw materials. The true genius of this process lies in its delivery system. While an impact would sterilize the surface, its fury is fleeting. The newly forged organic molecules raining down from the sky or protected in the turbulent wake would then be washed into the subsurface and oceans. There, in the relative safety of the deep, they could accumulate, mixing with the products from vents and radioactive beaches. Each catastrophic impact, rather than resetting the clock, was effectively restocking the planetary pantry. This turns the narrative of a hostile early Earth on its head. The chaos was not an obstacle to life's beginning, but its essential, relentless engine. The universe was not just delivering the building blocks via comets, it was also operating a giant, planetary-scale chemistry set, using asteroid impacts as its hammer to forge those blocks anew, over and over again. The true spark of life may have been the moment a molecule first meant something. This is the semiotic theory of life, a perspective that shifts our focus from chemistry to communication. It argues that the fundamental divide between a living organism and a non-living chemical soup is not the presence of complex molecules, but the emergence of meaning. Life began when certain molecules stopped being just physical objects and started functioning as signs, standing in for other things in a coded system of information. The most perfect example of this is the genetic code itself. A sequence of 3 nucleotides in your DNA, called a codon, holds no physical resemblance to the amino acid it represents. The codon AGC does not look like the amino acid serine. It is merely a symbol for it, an arbitrary sign agreed upon by the entire biological system. This is the essence of semiosis, the process of using signs, and it is the bedrock of all life as we know it. From this viewpoint, the first living entity was not the first cell or the first self-replicating RNA strand, but the first system where one molecule reliably pointed to another, creating a primitive language of interaction. This idea is profound because it is substrate independent. It does not matter if the information is written in DNA on Earth or in some unknown molecule on a distant world. What matters is the presence of that symbolic relationship. A living system is at its core a self-sustaining network of signs and interpretations, a conversation that began billions of years ago and has never ceased. This reframes the entire quest for life's origin, asking not what substance first stirred, but what message was first sent and understood. Life did not need a pre-made meal to get started. It could have cooked its own from the very beginning. This is the radical proposition of the acetyl-CoA pathway theory, which challenges a fundamental assumption about life's first menu. Most origin stories are heterotrophic, imagining the first organisms as consumers, scavenging amino acids and sugars from a probiotic soup. But this theory presents a different protagonist, an autotroph, a life form that built its complex molecules from the simplest ingredients in the atmosphere. The star of this story is a metabolic pathway still found in some of the most ancient bacteria and archaea on Earth. It is a simple, elegant chemical circuit that takes carbon dioxide and hydrogen gas and, with the help of common minerals like iron and nickel, transforms them into acetyl-CoA, a central building block for all of cellular machinery. The chemistry is so straightforward that it could have run entirely on its own without any complex genetic instructions. Iron-nickel sulfide minerals, abundant near hydrothermal vents, act as perfect natural catalysts, performing the same role that sophisticated enzymes do in modern cells. This paints a picture of life's dawn not as the sudden appearance of a replicating molecule, but as the ignition of a self-sustaining chemical cycle, a whirlpool of reactions that feeds itself and grows. In this metabolism-first world, the first life was not a thing you could hold, but a process you could observe, a persistent, swirling pattern in the geochemistry of a rock. Genetics, in this view, came later. Once a robust metabolic cycle was established, it became advantageous to develop a system to record these successful chemical recipes, leading to the evolution of RNA and DNA as a memory bank for the cell. This turns the traditional sequence on its head. Life did not begin with a genetic code that dictated metabolism. It began with a metabolism so successful that it eventually invented a code to remember itself by. Heat itself may have been the first fuel for life. The thermosynthesis theory proposes a beautifully simple engine for biology's dawn, one that ran on the planet's natural temperature swings. Before complex molecules learned to capture chemical energy or sunlight, the most primitive molecular structures could have been powered by the most abundant energy source of all, heat. Imagine a microscopic machine, a simple protein or a fatty acid vesicle, sitting in a tide pool or near a volcanic vent. As the sun rose, the water warmed, causing this tiny structure to expand. As night fell, it cooled and contracted. This relentless, rhythmic pulse of expansion and contraction could have acted like a pump, mechanically driving the synthesis of energy-storing molecules. This process, known as thermosynthesis, turns a passive object into a dynamic engine. The key player in modern cells is adenosine triphosphate, or ATP, the universal energy currency of all known life. ATP is like a tiny, rechargeable battery, and its formation requires energy. Thermosynthesis suggests that the earliest versions of this process were not chemical but physical. The mechanical stress from heating and cooling could have forced simple phosphate molecules to attach to other compounds, creating a primitive, energy-rich molecule that could then power other, more delicate reactions. This provides a stunningly universal starting point. Heat gradients are found everywhere in the universe, from the icy shadows of asteroids to the fiery plumes of gas giants. A system that can harness this fundamental physical force does not rely on a specific, pre-made chemical soup. It could have kick-started metabolism on any world with a day-night cycle or geothermal activity. The elegance of thermosynthesis lies in its minimalism. It does not require complex pigments for photosynthesis or intricate enzymes for chemical respiration. It needs only a structure that can physically respond to temperature change, a rhythmic environment, and time. This theory paints a picture of the very first life not as a chemical factory, but as a microscopic heat engine, patiently turning the planet's own heartbeat into the first sparks of biological work. Our evolutionary family tree may not have a single trunk, but an entire tangled thicket at its base. The last universal common ancestor, or LUCA, is a name that conjures an image of one lone, primitive cell from which all life descended. Yet a compelling theory dismantles this solitary figure, proposing instead that LUCA was not a single organism, but a bustling community. This was a world of progenotes, primitive cells with fluid genetic identities, constantly swapping genes through a process called horizontal gene transfer. Think of it not as a family tree, but as a massive, global collaborative project. In this ancient microbial network, genes for essential functions were not jealously guarded possessions but open source code, freely circulating and improving. A brilliant innovation for energy capture discovered by one cell could be rapidly shared with its neighbors, accelerating evolution at a staggering pace. This constant genetic barter allowed the core machinery of life, the genetic code itself and the fundamental processes of metabolism, to become standardized across the entire ecosystem. The evidence for this communal origin is written deep within our genes. When scientists compare the genomes of the most ancient lineages of bacteria and archaea, they find a puzzling mosaic. The genes for the most basic functions, like reading DNA and building proteins, are strikingly similar, suggesting a shared inheritance. Yet the genes for metabolism, for how these organisms eat and breathe, are wildly different. This is exactly what you would expect if life began as a communal pool where everyone used the same universal tools, but then specialized in their own ways of gathering energy once they started to diverge. This theory beautifully explains the deep and complex relationships between the three great domains of life. The first great evolutionary split was not a simple binary division. It was the moment when this communal, gene-swapping network began to solidify into distinct lineages. Some cells, the ancestors of bacteria, developed their unique cellular membranes. Others became archaea, and a later, monumental partnership between an archaeon and a bacterium gave rise to the complex cells of eukarya, the branch that would eventually include us. Our deepest ancestor, then, was not a winner in a brutal struggle, but a successful participant in a vast and ancient cooperative. Every living cell today runs on a universal energy currency called ATP. But this sophisticated molecule could not have simply appeared fully formed. The polyphosphate world theory offers a solution, proposing that the very first energy transactions were powered by a simpler, geologically abundant substance. Long chains of phosphate molecules, known as polyphosphates, are found in volcanic vents and can form through simple mineral reactions. These chains act like primitive batteries capable of storing and releasing chemical energy. Their availability would have been a game changer. Imagine the first attempts to build an RNA strand, a process that requires energy to link nucleotides together. A nearby source of polyphosphates could have provided the necessary spark, driving these crucial polymerization reactions forward. This ready-made energy source could have jump-started the entire process, making the leap from a soup of simple chemicals to complex, information-carrying molecules not just possible but probable. The theory elegantly connects geology to biology. Instead of a metabolism struggling to invent its own power source from scratch, the first protocells had a natural, external energy grid to plug into. This turns the origin of life from a mystery of spontaneous generation into a story of co-option, where biology learned to harness a geochemical gift that was already waiting in the rocks. The roar of the ancient oceans was more than just sound, it was a creative force. Within the thunder of every crashing wave and the hiss of every underwater geyser, countless microscopic bubbles formed and then violently collapsed. This process, known as cavitation, generated unimaginable conditions in an instant. For a fraction of a second, the heart of each imploding bubble became hotter than the surface of the sun, while the pressure soared to thousands of times that of our atmosphere. Yet this fury was contained and fleeting, a microscopic firecracker in a vast ocean. This theory proposes that these tiny, transient furnaces were the perfect crucibles for life's chemistry. The intense heat and pressure inside a collapsing bubble could have forced dissolved gases and simple organic molecules to fuse into more complex structures, like amino acids and the building blocks of RNA, all within the protective cradle of the water itself. This provided a continuous and widespread energy source, gentler than a lightning strike but far more common, turning the entire coastline into a chemical reactor. Laboratory experiments have brought this idea to life. Scientists have used powerful sound waves to create controlled cavitation in flasks of water containing simple chemicals. The result is not just noise but the spontaneous formation of complex organic molecules, proving that sound alone can act as a potent catalyst. It is a humbling thought that the relentless rhythm of the waves, a sound we find so peaceful today, may have been the relentless hammer that forged the first ingredients of life, molecule by molecule, in a billion tiny, imploding worlds. Carbon may be the foundation of our biology, but it had a rival waiting in the wings. Theory 27, the silicate world, asks us to consider a chemistry that never fully came to be. Silicon sits directly beneath carbon on the periodic table, sharing its ability to form 4 bonds and create chains and rings. On a young Earth still cooling from its violent formation, the surface was a searing landscape of molten rock and mineral vapors. In this inferno, carbon-based molecules would have been instantly destroyed, but silicates could have thrived. Imagine complex, crystal-like structures forming in the superheated magma, not as static minerals, but as dynamic, self-organizing systems. These silicate networks might have developed a primitive form of metabolism, channeling flows of energy and mineral components, and perhaps even replicating their intricate patterns in a slow geological dance. This would not have been life as we define it, but a kind of proto-life, a scaffold of stone. The true potential of this idea lies in a handoff. As the planet cooled and water condensed, this robust silicate world could have provided stable, mineral templates upon which the first fragile carbon molecules assembled. The intricate surfaces of these crystals might have acted as catalytic guides, organizing carbon and other elements into the very chains that would eventually form RNA, effectively seeding our own biological genesis from a foundation of rock. This highly speculative scenario forces our imagination to stretch beyond our own chemical bias. If a fleeting silicate biology could emerge and then pave the way for carbon life on Earth, what other chemical successions might be possible across the cosmos? On a scorching world where carbon is unstable, an entire, enduring biology of silicon might still be thriving, living a slow, fiery existence we can scarcely comprehend. The relentless heat of impacts and vents may not have been life's true cradle. A frigid beginning offered a different kind of advantage, pure stability. The psychrophilic origin theory posits that life did not ignite in a forge, but emerged from a deep freeze where the chaos of a warm world was replaced by a quiet, protective order. In the cold, organic molecules are not constantly battered by thermal energy. Destructive reactions slow to a crawl, allowing delicate structures like potential RNA strands to persist for millennia instead of shattering in moments. The key to this icy sanctuary lies within the ice itself. Even in the most frozen landscape, tiny pockets of liquid water can persist, trapped between ice crystals or warmed by the faint decay of radioactive elements. These microscopic, briny aquariums would have concentrated the building blocks of life, creating a perfect, secluded laboratory for chemistry. Within these pockets, molecules had the time and safety to explore stable configurations, to form bonds and complexify at a pace that a warm, turbulent ocean would never allow. Evidence for this frozen genesis comes from Earth's own polar extremes. In the bitter deserts of Antarctica, scientists find meteorites that have been preserved in the ice for millions of years, their complex organic cargo intact. They discover entire microbial ecosystems thriving within subglacial lakes like Lake Vostok, sealed off from the world for eons. The chemistry of these icy worlds is far from dormant, with slow, steady reactions occurring on the surfaces of mineral grains embedded in the ice. This theory reframes the very logic of life's start. The first spark did not need a burst of energy, but rather a sanctuary from energy's destructive power. For the first fragile, self-replicating systems, a slow and steady race in a frozen world may have been the only way to win, allowing life to gain a delicate foothold long before it was ready to face the fire. Our story of life's origin has often been told as a solitary struggle, a single molecule fighting to replicate itself against all odds. But what if the first life was never alone? The hologenome theory of evolution reframes this entire narrative, suggesting that cooperation, not competition, was the bedrock of our biological existence. This idea, usually applied to modern creatures like corals or humans whose health depends on trillions of microbes, can be projected back to the very beginning. It proposes that the fundamental unit of life was never a lone pioneer cell, but a collective, a collaborative consortium of different molecular systems and primitive cells from the very start. In this view, the first successful life form was not a single winner in a chemical battle, but an entire team that learned to work together. Picture the chaotic probiotic Earth with its thermal vents, tidal pools, and radioactive beaches. In these environments, you would not have had one perfect self-replicating RNA molecule. Instead, you would have had a bustling community of different molecules, each with a minor talent. One fatty acid vesicle might be particularly good at maintaining a stable internal environment. A nearby strand of RNA might be able to catalyze a simple reaction, but only if it was protected inside that vesicle. A third system, perhaps a mineral surface, could be supplying a steady trickle of energy. Individually, these were just interesting bits of chemistry. But together, they crossed the threshold. The vesicle provided the home, the RNA managed a primitive function, and the energy source powered it all. Their collaboration created a stable, self-sustaining whole that was far greater than the sum of its parts. This systems-level view directly challenges the selfish gene narrative that has dominated our thinking for decades. It suggests that the drive to form partnerships, to merge and cooperate, is not a late evolutionary development but the very mechanism that allowed life to ignite. Symbiosis was not an afterthought, it was the founding principle. The first genetic code may have emerged not as a tool for one molecule to dominate, but as a common language that allowed these different molecular societies to coordinate their efforts, to share resources and information for their mutual survival. The profound implication is that we are not the descendants of a single triumphant molecule, but the heirs to an ancient and enduring partnership, a legacy of collaboration written into the first chapter of life itself. The boundary between the observer and the observed begins to dissolve in the final theory. Drawing from the most enigmatic interpretations of quantum mechanics, this hypothesis proposes that consciousness is not a mere byproduct of life, but its fundamental precursor. In the quantum realm, a particle exists not as a single point, but as a cloud of probabilities, a wave of potentialities. It is only when this system is measured, when it is observed, that it snaps into a definite state. Some physicists and philosophers extend this principle to the cosmic scale, suggesting that the entire universe existed in a fuzzy, unrealized state until the first glimmer of awareness caused reality to crystallize into being. From this vantage point, life did not emerge into a ready-made universe. Instead, the universe and life co-awakened in a single, inseparable act. The origin of the first living organism was not a chemical fluke, but the moment the cosmos became capable of looking back at itself, of experiencing its own existence. This idea shatters our conventional categories. It posits that even the simplest bacterium possesses a minute degree of this cosmic consciousness, a capacity to interact with and define its reality at the most basic level. The spark of life was not a lightning strike in a pond, but the universe opening its eyes for the first time. This is the most philosophical and controversial of all the theories, a profound blurring of the lines that separate physics from biology and matter from mind. It reframes our entire search for meaning, suggesting we are not just inhabitants of the cosmos, but the very process by which the cosmos knows itself. We have traveled from the deep sea vents to the cosmic dust of panspermia, and from the quantum realm to the very nature of consciousness. The sheer number of possibilities is not a sign of failure, but a testament to the profound creativity of the scientific mind. Each idea, from the warm little pond to the frozen psychrophilic beginning, is a different lens through which to view that singular, monumental event. They are not necessarily mutually exclusive either. A comet could have delivered PN to a radioactive beach where it was concentrated on clay and energized by thermosynthesis, all within a collaborative hologenome. The true answer may be a tapestry woven from many of these threads. The value lies not in finding one definitive victor, but in the journey of asking the question itself. This pursuit forces us to challenge our definitions of life, to expand our understanding of the universe, and to appreciate the staggering improbability and yet the persistent drive of existence. So we turn the question over to you. Which of these worlds feels most like home for life's first spark? Was it the chemical rhythm on a pyrite crystal, the quiet replication in an icy pocket, or something else entirely? Share your thoughts in the comments below, and if you enjoyed this journey to the very beginning, be sure to like, subscribe, and tap the bell for more explorations into the universe's greatest mysteries.